Consider the solution to the seesaw problem from exam 1. All right, so one of the things we looked at was when we solve these kind of problems, we draw a free body diagram. Okay, so we have this weight W2. We have this weight W1. And at the pivot point, we would have a force. We're assuming the mass of the beam is negligible compared to the weight of the riders on the seesaw. All right, so what I know is that this force moving up is equal to the forces going down. All right, so that's actually the answer to 25. We know that the weight of the adult is 180 pounds, the weight of the child is 60 pounds. So at the pivot point, that's the support force that's required to hold up the teeter-totter. So we know that one. All right, so next what we need to do is figure out what the forces should be, or what the length L2 should be to balance the forces. All right, so one way we could do that is to do sum of moments about the pivot point P. Okay, and so we know this distance to P is L1, and this distance, this perpendicular distance to the force in this direction is L2. All right, so sum of moments about the point P. All right, so W1 would cause a counterclockwise rotation, so this would be W1 L1. Okay, and W2 would cause a clockwise rotation, so that moment would be negative minus L2 W2. So the sum of moments is equal to 0, and so we have this equation. All right, so we're given W1, we're given L1, we're given W2. We can solve for L2, and when we do that, it's pretty straightforward to solve that. You get 6 feet as the answer. Okay, next, take the same teeter-totter problem with the distances L1 and L2 that you solved before, L1 and L2, okay? And then look at what happens if you simultaneously sat on the seesaw under this condition, okay? So one thing you need to do is think about how you would solve this problem. You draw a free body diagram. Okay, so again, this is tilted up at an angle theta, and so this angle is also theta. All right, and so again, we have a force operating at the pivot point, a weight W2, a weight W1, and even though this is tilted, the sum of forces of W2 and W1 is equal to F. So no change there. All right, so the question is, what happens to the moments? All right, well, remember, you take the line of action. All right, so here's the line of action of W2, and so I could calculate that perpendicular distance. That would be sine, if this is theta, this would be, cosine. Cosine theta, all right, times L2. Remember, this distance is L2. All right, so this total distance, this perpendicular distance is cosine theta L2 times W2. That is the moment that's generated by W2 about point P. And it's clockwise rotation, so that'd have a minus sign. Okay? And then you do the same thing for theta 1, all right? So this perpendicular distance is also going to be cosine theta, L1, W1. This rotation is counterclockwise, so it would be positive. So we have this equation that's equal to 0. So we could solve that equation. Cosine theta L1, W1 is equal to cosine theta L2, W2, and the cosines divide out, so the fact that it's tilted didn't really matter. So if it was balanced at L1, W1, like it was in the previous part, then nothing else is going to change. Okay, it's in equilibrium, so there's no motion that would happen. So the answer here is part C.